Hardware is organized into abstraction layers. We've so far been looking mainly at the high-level abstractions, things like the motherboard and the integrated circuits. In this presentation, we want to take a closer look at some of the lower-level ones, including the gates and the flip-flops that make up the primary computational components. At the lowest abstraction layer are the physical electronic circuits. These are composed of transistors, the fundamental building blocks of all electronic devices. And transistors and the other materials, such as the silicon chips the circuits are printed on, are designed by physicists and electrical engineers. But all electronic devices contain circuits and transistors. It's the next level up where we start seeing the main computational components, gates and flip-flops. Gates are small electronic circuits that make decisions, the kinds of decisions you find in your I Have a Dream app. Similarly, flip-flops are the basic memory components. These computational components can be integrated into circuits, put into integrated circuits, which are otherwise known as chips. In this case, we're looking at a central processing chip. And these chips have functions, such as memory or a processor or a GPS. And they are integrated together at the highest level on the motherboard, where they're organized into a computer system. Let's now look at some of these computational components. A gate is a tiny electronic component that performs a basic logic operation. For example, here's a circuit diagram of an AND gate. An AND gate is one in which the light would be on only when both switches A and B are on. So A and B represent the inputs and the light represents the output. The output is on when both inputs are on. We can represent this behavior as a logic function, a Boolean function as it's called after the mathematician who developed Boolean logic. And the truth table shown here is the fundamental way of defining this type of component. So what the truth table says is that when A and B are true, represented by ones here in the fourth row, then the output will be true, and it's false in all other cases. So the logic truth table is an abstraction of what's happening in the physical circuit. We can take the abstraction one level further and represent the logic by this simple symbol here. This is the symbol for an AND gate. It takes two inputs and one output, and we know that this output is on or true only when both of the inputs are on or true. And we can look at now the abstractions for the AND gate as three different levels of abstractions. At the low level, we have the physical circuit, represented by voltages and transistors and switches. At the mid-level, we can view that more abstractly as a truth table function, which defines the output given every possible input. At the highest level, we can dispense with the details and simply refer to an AND gate by its symbol. Now, why would we want to do that? Well, once you know that this symbol means what's expressed in this table, you know the definition of an AND gate. You don't need to write it down when you're designing more complex models and more complex designs. The OR gate is another fundamental computational component. The OR gate, the light goes on when either switch is on or when both are on. And we can define that by defining a truth table. And what this truth table says is that the output of the OR gate will be 1, which is true or on, whenever either input is on or both are on. In fact, the only time an OR gate's output is false or off is when both inputs are off. And similarly to the AND gate, we can represent the OR gate with a symbol. Finally, we have another basic electronic component, the NOT gate. The NOT gate simply reverses its input. If the input is false, it makes it true. If it's true, it makes it false. Amazingly, all electronic components are built out of these three basic gates. For example, the NAND gate is a combination of the AND gate and a NOT gate. Similarly, a NOR gate is a combination of a OR gate and a NOT gate. So as you can see, we can build up bigger abstractions by combining together our lower level abstraction. This is an example of a flip-flop or a latch. It's a circuit that has two states, and the states represent one bit of data. either a 0 or a 1. And the way it works is this. When you reset it, meaning you put high voltage on the reset input, that changes the bit stored in here into a 0, and it stays there. On the other hand, when you set it by putting voltage or high input on the set line, that changes the bit stored here to a 1, and it remains 1. So this is the fundamental memory unit that makes up the memory chips that we looked at. And that's a quick look under the hood.